So we have actually entered into an era of information. And in the last session, we were discussing about two important components of this information age. The first was the transmitter part, and the second was the receiver part. In the transmitter part, we have the photonic equipments like LED, light emitting diodes, and semiconductor lasers. And on the other side, the receiver side, we have, for example, a detector, photodetectors, either PN junction photodiode or PIN photodiode, and there are 1,000 other possibilities. Now, today, we are going to discuss about the channel connecting these two particular sessions, the receiver unit and the transmitter unit and the receiver unit of this photonic revolution or information revolution. Now, we are very proud to say that an Indian has contributed, Indian is called the father of this particular optical fiber, and he has coined a word, a term to describe this technology, fiber optics. So he was a Punjabi person, and he migrated to England for his studies in the Imperial College already in 1952. He developed this particular concept, and he did a lot of experiments on some fibers, inspired by a very old idea by John Tyndall. What John Tyndall observed was the possibility of bending light being bent when it's passing through a water jet. So the fundamental idea is something which is well known. You have studied in small classes, there could be total internal reflection. When a light is traveling from, two conditions we have already defined for total internal reflection in small classes. The first condition is that light should travel from a denser medium to a rarer medium. So let's draw that. Let's imagine you have a medium N1 and medium N2, whose interface is this line, and under the condition N1 is greater than N2, which means this is optically denser region, this is optically rarer medium. Now, if you allow a light to fall on this interface, you know there will be an angle created here. This is called angle of incidence. Let's imagine this angle of incidence is less than a critical angle, theta c. Then this particular light, so this is being rarer, it will be bending away from the normal, so it will be bending like this. So this is the angle of refraction. Obeying the famous law, which we all know, this is Snell's law. So there will be two medium and two angles. This is angle of refraction, theta r. And now, if you consider a greater angle for incidence, let's say this is happening here, and let's say this particular angle theta I, angle of incidence, is equal to a particular angle which we call critical angle. I will come to that, why it is called critical angle. So this particular ray will be making a angle of refraction which is 90 degree, which means the light does not pass through the rarer medium, rather it will be grazing the interface between this medium. And that happens at a particular angle which we name critical angle. And this is important to understand what is critical. When we use the word critical in physics, it means there is a total change in the phenomena. We have seen the first sessions, we spoke about, for example, critical temperature or critical field with respect to superconductivity. And we know these two critical temperature and critical field. This speaks about a phase change from a normal conducting state to superconducting state. And when we discuss about the LED and semiconductor laser, we found a critical current. And that current was a critical point where LED becomes a semiconductor laser, which means the linear increase in the power, which is characteristic of a LED, which will be changed over to exponential explosion of the power, which is characteristic of a laser. So similarly here, so far we were using the laws of refraction. The laws of refraction, as you know, is the Snell's law, and you know that is n1 sin theta r is equal to n2, n1 sin theta I is equal to n2 sin theta r. That's going to be the Snell's law. And now, let's imagine what will happen if you increase this angle. This is angle of incidence once again, but in this case it is greater than theta c, a critical angle. Now the phenomena changes. So far, the phenomena was refraction. Now from now on, the law will be law of reflection. So which means, what is law of reflection? Angle of incidence will be equal to angle of reflection. So, I use same words, or reflection. So there's a total change in phenomena. So that is why this particular angle is now called a critical angle. It's an angle below which, or at which there's a change of physical law of light. The physical law till here was a refraction. Now from now on, this particular light ray will obey the law of reflection. So I just wanted to bring you to the use of the meaning of the use of the word critical in physics. So in these particular sessions, we use that many a time. That's why I just want to specify that. Now, there's something very fantastic from this picture. You can already see the light is traveling from a denser medium to rarer medium. So corresponding to your idea about the conditions of total internal reflection, so the first condition was that light travels from a denser to rarer medium. And second one was that the angle of incidence at this interface should be an angle greater than critical angle. If both conditions are satisfied, we say that total internal reflection will happen. And this is therefore, this means that light will not anymore enter this particular second medium. Light will remain in this particular medium, which is called N1. This is a fantastic idea. So you get an idea how to confine light, how to guide light through a particular channel. That is an important concept which we get by this total internal reflection. So our Narendra Singh Kapani, he was a very successful engineer with more than 100 patents in this particular area. Now he understood the power of this particular idea, and he already developed something which I am going to draw. This is what is called the basic structure of an optical fiber. So we have, for example, a region which you call optical core with higher value of refractive index, N1, and you have a surroundings. You should imagine this is a three-dimensional structure. So this is a wire-like stuff. So you have now cladding, which is having a refractive index which is smaller than this. So N1 greater than N2. Now, let's say this is the axis of this particular optical fiber. Now, if you send a light to this in such a way that at this particular interface between core and cladding, the angle of incidence is greater than critical angle. Then what will happen? Light will totally internally reflect, not just once. Here again, the same condition will be met, conditions for total internal reflection. So it will be reflecting back, and like this, multiple total internal reflection will be there, and the light will be entirely confined in this particular channel, which we call core. So confinement of light into the optical core of the optical fiber is the idea that Narendra Singh Kapani had. He even, in his days, he could even allow a image to be transmitted through optical fiber. The information about a image could be, he could transmit through this optical fiber. So that is a very wonderful achievement by an Indian. But there was a major problem. The major problem was that the light which is passing through this optical fiber core was get lost very soon. Its intensity got lost, which means there was a lot of attenuation losses for this light. So the maximum distance could transmit this particular information 20 meters. Now, there was another important person which is called, whose name is Charles Kao. He was working in the Chinese University of Hong Kong, and he started working already in 1960s, and in his lifetime, he achieved a tremendous improvement for this distance of transmission. From 20 meters, he made it 100 kilometers. So there's a big achievement this man has made, and rightly he has got Nobel Prize in this for this improvement. He got Nobel Prize in 2009. Very recently he got Nobel Prize. He died already, but Narendra Singh lives. Narendra Singh did not get Nobel Prize. He is an unsung hero in this technology, but at the same time, Charles Kao made a real breakthrough. It could be called maybe the godfather of broadband. The current technology, the technological level of this fiber optics was drastically improved by Charles Kao. What he found was interesting. You know, I have already mentioned there is a core and cladding. Now, he found that the major reason for the loss of intensity when light passes through the optical fiber core is the purity of the material used here. The glass material, generally glass materials are used. So if you could improve the purity, the intensity losses or attenuation losses can be drastically reduced. That is how he could allow the light to travel long distances without much intensity losses or attenuation losses. So these names you should remember. Therefore, when we think about fiber optics, we have Narendra Singh Kapani, an Indian, and John Tindall was inspiring him, and Charles Kao got Nobel Prize. So we start with a Nobel Prize winner to be inspired to understand this particular technology, which is called fiber optics. Let us now discuss about the numerical aperture of an optical fiber. You know, numerical aperture is a quantity which is not specific to optical fiber. This is a general term which is used for all kind of optical instruments. Essentially, it is the ability of that particular optical instrument to gather light. Light gathering capacity of that optical instrument. In our case, it is the light gathering capacity of the optical fiber. This is very important to know because of the optical information this particular optical fiber has to carry later on. We will come to that later. Now let's derive a simple expression for numerical aperture for an optical fiber. As we have already discussed, we have optical fiber fundamentally made of a core which is having greater value for refractive index, surrounded by a cladding which is having a lower value for refractive index, and this is the optical fiber axis. Now let's imagine the surrounding medium is ambient. So there is ambient has a refractive index. It could be ambient, could be air, any other medium, oil, water, whatever it be. They generally call it ambient. And you know, the minimum condition of confinement of light in the optical core, that is what we actually want, is that at this particular point, the ray that is entering this particular optical fiber should at least graze the interface between the core and cladding. That's the minimum condition for confinement. Let's start from there. And if that is happening, we know this particular angle is 90-degree angle of refraction. Let's come back, let's just draw it back. So, which means, you can have a, here corresponding angle will be critical angle. We have already seen that when the angle of incidence at a particular interface is at xc, this particular refractor ray will be grazing the interface. So, that is the condition we are deriving. So, you can imagine this angle is 90-degree, and let's say this is alpha prime, some value. But this light has to be input from outside, from the ambient, to this optical fiber. So, let's trace it back. This is let's suppose this medium is a rarer medium, and this here is optical fiber core, which is a denser medium. So, of course, then we find a bending towards this this particular the normal at the point of incidence. That this is the normal, which we call the axis of the optical fiber, is the normal at the point of incidence. Now we get an idea about a maximum angle which is acceptable to send this light to this optical fiber core, with the minimum expectation that this particular light will at least graze the interface of core and cladding. So, this is a maximum, because if you just imagine if you are sending a ray which is having a greater angle than this, then what will happen here is that it will be leaking into the optical cladding. So, this is something which we don't want to have. So, this is the maximum angle. So, we have a maximum angle here, which we can call alpha m. This is generally called acceptance angle, fiber acceptance angle. So, if light is falling at least this particular angle or lower values, that is the acceptable angle. And you should also imagine that this particular structure, we have made it a two-dimensional picture, but it's in fact a three-dimensional material. It's a wire-like stuff. Therefore, you could imagine this particular angle is not a plane angle, rather a angle of a cone. In fact, a half conical angle. This is the full cone. You have a full cone here where the light could enter. Now, this will be half conical angle. So, we are discussing about a fiber acceptance angle, which means, as I told you, that's the maximum value of the angular incidence from the ambient. If you send the light information into this particular optical fiber at this angle, that's the minimum condition for being confined, that particular light being confined in this particular optical fiber core. So, from this understanding, let's try to define what is called derive an expression for numerical aperture. As I told you, numerical aperture is the ability, it measures the ability of this optical fiber right now to gather light. And we have two interfaces to consider where refraction is taking place. Let's consider, to start with, ambient core interface, so which means this interface. So, ambient core interface. Now, you have a Snell's law there, and Snell's law will be NA, that's the refractiveness of the ambient, sine alpha m is equal to refractiveness of the core N1, and the angle of refraction here in the denser medium, sine alpha prime. Now you know the total angle of a triangle is 180. You have 90 here, and this angle should share 90. So therefore, alpha prime will be 90 minus theta c. So you can write equivalently, this is equal to n1 sine 90 minus theta c. So sine 90 minus theta c, as you know, this is cos theta c. So n1 cos theta c. Now cos theta c you can write in terms of sine theta c as n1 square root of 1 minus sine square theta c. And there is a purpose, you know, Snell's law will be always containing sine. So therefore, you can have the definition for theta c, sine theta c, from the second interface. So let's go to the second interface. So that is the interface between core and cladding. Let's write the same Snell's law for core cladding interface. So you can easily see that the Snell's law will be n1 sine theta c. This is the angle of incidence at the interface between core and cladding will be equal to n2, which is the refractiveness of the cladding, sine 90. Sine 90 because you know this is the condition for grazing the interface. So sine 90 is 1, and therefore sine theta c will be nothing but n2 minus n1. Substituting here, you will get this is equal to n1 square root of, you can take it to the, so 1 minus n2 square minus n1 square, which is you can bring the n1 here, n1 square will be cancelling with the n1 in the outside. So therefore, you will get this is equal to square root of n1 square minus n2 square. So this is the expression for NA sine alpha m. Now you know how we define the numerical aperture. Numerical aperture is defined as a sine function of this particular fiber acceptance angle, which is the alpha m. So what you have, numerical aperture is sine alpha m. It is here, therefore you can write numerical aperture is equal to square root of n1 square minus n2 square divided by NA. So you can easily see the numerical aperture is a function of core refractive index, cladding refractive index, and the refractive index of the ambient. And let's imagine the ambient is air, which is normally the case. So in that particular case, it will be equal to n1 square minus n2 square. You can write as n1 plus n2 into n2. So which means the refractiveness of the core and cladding will radically determine the fiber acceptance angle and the sign of that fiber acceptance angle, which is numerical aperture. Which means something interesting, that you cannot put light at any desired angle. The mouth of the optical fiber is not open 90 degree like the mouth of a crocodile. Rather, it will be open with a minimum opening will be there. You can imagine you have a friend, you want to throw chocolates into his mouth, and you cannot catch all these chocolates because his mouth is not infinitely open. There's an angle for the opening, maybe 20 degree, 30 degree, that's the maximum it can be open. So is an optical fiber. If you want to input a lot of information into this optical fiber, it is not possible that, you should imagine that this optical fiber is incapable of receiving it because it cannot open its mouth greater than alpha m in such a way that the light will be able to be captured and propagated through the optical fiber core, or confine the light to the optical fiber core. So this is the basic concept of optical fiber right now. And in fact, we have done an experiment in this regard in the lab. So we know the refractive index of the usually the technical information about an optical fiber, give the values of the refractiveness of the core and refractiveness of the cladding. So you can easily calculate the numerical aperture using this expression n1 square minus square root of n1 square minus n2 square. So it's very easy. But you know, the measurement of n1 and n2 is very tricky because its difference will be very small only. Therefore, practically, if you calculate like this, it may not be really applicable in practice. So therefore, what we do is that we just send light, and at the output side, you can have you can put a screen where a circle, a cross section of this optical fiber cone will be made, which will be having a shape of a circle. So from that, you can easily calculate the fiber acceptance angle. You know, let's say this is the fiber acceptance angle, this is the alpha m, the maximum angle, and let's say this particular circle, which is a cross section, which is a trace of this cone on a surface, the radius is r, and let's say the distance between this optical fiber core and this particular screen which you have put is L. So you can have alpha m is equal to tan inverse of r by L. But you know, generally angles are small, so you can even write this is equal to r by L. And you can calculate alpha m, and you can calculate sine of this alpha m, which is nothing but the numerical aperture. So you can practically measure this numerical aperture in the lab, and you are already doing this particular experiment in the lab. So let me tell you a few more things in this connection. We have seen a particular minimum condition. This is the minimum condition for opening of this optical fiber core, for propagation of this light through this optical fiber core, confined to the optical fiber core. Now let's see what will happen when the angles are, for example, greater than that. We have already seen if the angle of this cone is greater than, if you throw information into this particular optical fiber core at an angle greater than alpha m, what happens is clear. We have already seen that. The light will be refracted at this interface between ambient and core, and it will be again refracted at the core cladding interface, and it will be leaking. Leaking to the cladding. Leaking to the cladding means that information is lost, intensity of light is lost, and this particular information is lost, attenuation loss will be happening. So we cannot accept that, because we want this light to be confined and propagated through this optical fiber for long distances. So the minimum condition is that the alpha m. So what will happen? It will graze, this particular light will be grazing the interface between core and cladding, which is acceptable. Now let's say this particular angle is 0, which means light is passing through the optical fiber axis. So that is excellent thing, because there's no refractions, nothing happening. This is falling normal to this, and will be passing through, okay, through the optical fiber axis. Now let's take an angle very close to this axis. What will happen is that, you know, it will take long paths like this, very few number of reflections, and therefore light will be passing through the optical fiber core. And now let's take another case which is very close to alpha m. What happens is that light will make a lot more reflections, total then reflections, before it is leaving this is the way it will be propagated through the optical fiber. So there are three possibilities, three types of possibilities. So you can name this particular, there are different optical paths to the optical fiber core. So you can say there is an axial mode. To start with, axial mode means a path. So there is a path through the axis, okay? A path through the axis. And second one is very closer to the axis, which is making very few reflections and for passing through, which means this is making a lower order order mode. So there's another type of path. The first type of path is the axial mode, which is passing the axis of the optical fiber, and which is very close to the axis, which makes few number of reflections for propagation, so lower order mode. Other one, which is very closer to the alpha m, it makes large number of internal reflections for passing, so you can call this higher order mode. So there are three types of paths. So in fact, axial mode is just one mode, but lower order modes and higher order modes, there are different numbers for that. But there's a typical characteristic for this. You can understand the axial mode will be the shortest path. The shortest path will be axial mode for propagation. And the lower order mode, which is starting very closer to this particular axis, will be in between path. That with respect to distance, it will be in between. And you have a longer, the higher order mode, which means large number of reflections for propagation, which means that path will be the longest. So you have the shortest path through the axis, the longest path for the higher order mode, and in between a medium path through the lower order modes. So now, this is interesting to observe because we have to consider what kind of information you are going to give to this optical fiber. In the digital era, information is everything digital. We have electrical bits. For example, we say there is a 0 and 1. Electrically, it means 0 means a low voltage and 1 means a high voltage. So every information we will be converting to zeros and ones. And 0, once again, this is the lower voltage and 1 is the higher voltage. Now, when it comes to the optical digital communication, we should think about optical bits. What is optical bit? Optical 0 is off, no light, off. And optical 1 is on. So which means what kind of information we are going to give to the optical fiber mouth? On, off, or off, on. A series of zeros and ones. Every time 0 is off, 1 is on. Now we should imagine what will happen to this light which is entering to this optical fiber core. On, off, such information. When light is on, you should imagine that on, the light travels through different paths. There's a shortest path light travels, longest path, higher order mode, in between, lower order mode. So light on, when it is on, light travels through different paths. What's the problem then? If it travels long distances, you can imagine, we speak about kilometers, there will be a problem, a critical problem, which means your off and on will be mutually confusing. Because one part of the on is traveling through axial mode, they'll be traveling faster. Another part is traveling through a lower order mode, which is in medium path, and another part of this on information is passing through the higher order mode. So there will be a flattening effect for this particular on, a pulse. So flattening means it will be looking like a 0. So you cannot anymore distinguish between zeros and ones. This is what is the major problem for the optical fiber communication. So this is called the dispersion losses. Dispersion losses means you cannot anymore distinguish between zeros and ones. They are all, a general lighting will be there. The information will be washed out. So you cannot allow the information to be washed out because that is the core, what we want to get transmitted through the optical fiber core. So therefore, you cannot afford to go to that particular level. Therefore, care must be taken for avoiding this kind of problem. So I just conclude by saying we have discussed about numerical aperture, light gathering capacity, and we have derived a half conical angle at the optical fiber mouth or optical fiber end. Both are equivalent for an optical fiber, mouth and the end, or both are equivalent. So this is acceptable angle for optical fiber transmission or propagation of light through the optical fiber core. Now, we also discussed about different possibilities. If the light enters this particular optical fiber at a greater angle, alpha m, they get lost. Intensity losses or attenuation losses will happen. Now, the region between 0 and alpha m, that is the only possibility. So, but there is an axis, the 0 angle is the shortest path, and longest path will be the higher order mode. It's very closer to the alpha m, and lower order mode is also there, which is a medium path. But the problem right now is to receive this optical, when on receiving on-off information can be flattened, or information can get lost as a general illumination, so which cannot be afforded. So these are the important points we should take care when we discuss about numerical aperture and fiber. So now let's discuss about the different types of optical fibers which are available. OFC is the name, it is shortened called optical fiber cable. So OFCs can be of different types. These types are distinguished by the distribution of the refractive index of the core and cladding, and with the number of modes. I have already explained the meaning of the mode, number of paths through the optical fiber. Now let's start with what we have in the middle. This is what is called step index multi-mode optical fiber. So by step index, we mean the core and cladding refractive index will be both constants. There will be one value, higher value for the core refractive index, and one lower value for the core cladding refractive index. So N1 and N2 are constants, and therefore when we draw the profile of the refractive index, starting from the axis of this optical fiber where we put 0, and we move in the radial distance, we find this is the function drawn as a function of the refractive index. You have a constant value for the refractive index of the core, a higher value, and a lower constant value for the refractive index of the cladding. So this looks like a step. That is why this particular type of optical fiber cable, OFC, is called step index optical fiber. Now, this is also called multi-mode due to one important reason. So you can see this particular optical fiber core will be having approximately 50 micrometer, which means rather large core. The large core also means that depending on the alpha m, that there could be different types of modes, different types of paths through this optical fiber core. There could be a path through the axis of the core, as we have already seen, and higher order mode, which is near to the alpha m, and a lower order mode, which is with incidence angle, which is closer to the axis. So different types of modes will be there. Large number of modes, large number of optical paths will be there through the optical fiber. And I have already told you, this is not going to be a positive thing for optical fiber. If there are large number of paths like that, if you have an on signal coming, what will happen? One part of this particular signal will be traveling through the axial mode with the shortest path, and another part of the same signal will be traveling through the longest path, which is defined by higher order mode, and yet another part of the signal will be traveling through the lower order mode. So which means the same signal is traveling through different paths which are having different lengths. So therefore, at the end of this particular optical fiber, after a short distance, what will happen? There will be only general illumination. The signal, the bit, the data is lost, the information is lost, which we cannot afford, because this is communication, where the signals are important and signals has to keep their shape. Whether it is 1, it is 1. We should be able to distinguish between zeros and ones, which will not be made allowed if there is a lot of dispersions, loss of shape, flattening of these pulses as they travel different distances in time. So this is technically very easy to make because of this core diameter, which is large. To develop core diameters, optical fibers with core diameters large is easier. The technological challenge will be to reduce this optical fiber core diameter so that you can avoid all these different modes. So not everywhere that if you have many, it is advantages for us. If you have multi-mode, this is giving a disadvantage for us. And because of this particular problem, we'll be challenged to reduce the number of bits which can be passed through this particular step index multimode optical fiber. Because in order to be able to distinguish between on and off, optical 1 and optical 0, we'll have to introduce bit intervals. So some region, so you have 1 and an interval, then 0, and then 1, like that, So you cannot propagate, we cannot put input a signal at any rate. So therefore, the bit rate will be suffering, and generally the bit rate which can be passing through a step index multimode optical fiber will be less than 500 Mbps. Megabits per second, Mbps. This is something which we already know. So, therefore, to overcome this technological barrier, the immediate thing we could think about is to reduce the core diameter. So, let's say we are going to reduce a core diameter to, for example, 10 micrometer, 5 times smaller. So, such kind of optical fibers are called step index single mode optical fiber, which means that no different types of modes are allowed anymore. Rather, one single mode is allowed to pass through this optical fiber core, and that path, mode means path, that path will be the axial path, axial mode. So light will be traveling only through the axial mode. The advantage being, since there are no different paths with the different lengths and different transit times, the shape of the pulse will be intact. Which means if you give a pulse on, optical on, it will be optical on, through and through. Because there is no flattening of this pulse, loss of shape of this pulse. So you can, therefore, it will be possible for you to give large bit rates. Large number of bits can be passed through this particular optical fiber core. Generally, the bit rate will be greater than 1 gigabits per second. So great bit rates can be achieved. We just reduce this the diameter of the optical fiber core. But it's a technical challenge because you should imagine 10 micrometer means much smaller, thinner than your hair. So the production of it, the manufacturing or the technology behind it will be very complicated and it will be extremely expensive because of that. Therefore, wherever possible, we have to modify this kind of optical fiber, optical fiber core in order to achieve the same effect. For example, can we somehow, without reducing the diameter of the optical fiber core, is it possible for us to achieve the equalization of the transit time? And that is achieved by a greater index optical fiber, where you have the same core diameter, say 50 micrometer, but we are making a small modification. The modification being, the index of the refractive index of the core is having a parabolic structure, which means along the axis, it will be achieving maximum value. So refractive index is defined as a function of radial distance. When radial distance, this is 0, radial distance is 0, it will be having maximum value. And it moves from axial axis, which is at 0, in the along the radial distance to the core cladding interface. Refractive index is gradually decreasing, which means the shortest path, which is the axial path, will be having greatest value for the refractive index. So in other words, the shortest path will be the slowest path. You know, the speed of light will be depending on the refractive index, and if the refractive index is very high and maximum, that path will be the slowest. Axial path, axial mode is the shortest path, but that shortest path will be having greater value for the refractive index, and it will be slowest path. Now, I have already told you another types of paths, higher order paths and lower order paths. Higher order paths will be making large number of reflections, and it will be crossing very much this region between near to the core cladding interface, and that path is longest path. But you know, near the core cladding interface, the refractive index is very small. So in other words, the longest path will be the fastest path. The shortest path is the slowest, and the shortest path, the longest path will be the fastest, which creates a situation that whichever path you take, that there will be the transit time of the pulse. For example, if you give a 1 here, it will be transiting through this optical fiber core at the same time. There's an equalization of the transit time. And that is another way, an ingenious way to avoid intermodal dispersion, which is very much there in the step index multimode optical fiber. So this is a brilliant idea. So in order, we don't want to reduce the diameter of the core, rather we make this the core as a graded index. So we give a graded index profile. Graded index means maximum value we give to the optical fiber core, and gradually decreasing value for the refractive index for the, so refractive index will be a function of R, a decreasing function of R. So as the R increases, refractive index decreases. So this is an ingenious idea. So the technical difficulty of making the core diameter smaller is avoided, but new technological challenge is coming here, additional technological challenge. There will be smooth variation of this particular refractive index, keeping maximum value for the axial mode, axial path, and as we move away radially to the core cladding interface, the value of the refractive index should be gradually decreasing. Stop. So we have already seen the refractive index profiles of this particular different types of optical fibers. Now let's see how I've just verbally mentioned. Now pictorially, let us see what is actually happening within this multi-mode step index optical fiber, single mode step index optical fiber, and graded index multi-mode optical fiber. So in the step index multi-mode optical fiber, as I've told you, there are different types of modes. The axial mode is the shortest path, and a path very closer to alpha m, the fiber acceptance angle. It will be making large number of total line reflections at different points for propagation, which will itself make the longest path. And another type of optical path is very closer to the angle of incidence is very small and very close to the axis. So you can see that it will make very few total line reflections for propagation. So that will be creating a medium path. So they are not just one, three, rather three types of types of modes, types of path. Axial mode is one, but higher order mode and lower order mode are large in number. So the problem here, I've told you, the light, the optical data is zeros and ones, on, off, 1 and 0, on, off. Now let's say the on information, one pulse is divided into different paths. One part of the pulse will be traveling through the optical fiber axis. Another part of the pulse will be choosing the higher order mode. And yet another part of this signal will be carried by the lower order mode. So therefore different paths, and therefore the bit will be stretched, and we'll just get a general illumination, and the distinguishability of zeros and ones will be lost, which in effect is the loss of information, which cannot be afforded. Therefore, what we do is that between these bits, we give a extra interval, and therefore the net interval, net bits, which we can pass through this particular step index multimode optical fiber will be always less than 500 megabits per second. But that problem, as I told you, is solved by reducing the core diameter maybe 5 times smaller. Here it was 50 micrometer, and here it is 10 micrometer. Then we could eliminate all other modes, excepting the axial mode. So there will be only one path. And the entire pulse, whether it is on or off, it will be clearly, distinguishably passing through this optical fiber. Therefore, we need not, there's an intermodal dispersion or the broadening of pulse due to different paths. That problem is solved here. And therefore, we can really go beyond 1 gigabits per second. Great values we can go for the bit rate. Now, the same problem is solved in another way by making the index, the core index graded manner, where you give maximum value for the maximum refractive index value for the optical fiber core axis. And as you go from the axis to the radially to the core cladding interface, refractive index is gradually decreasing. So you know the refractive index, as I told you, is a measure of the speed of light. If the refractive index is very high, it means the speed is slow. Light will be traveling at a lower speed. Therefore, the shortest path, which is the axial path, will be the slowest path, because refractive index there is the maximum. And the longest path, which is the higher order modes, they'll be traveling faster, because refractive index is smaller there on an average. And the lower order mode path will be also traveling adjusting its speeds. So the net effect is that there is an equalization of the transit time. Every bit, 1 or 0, they will travel through the different, even though it travels through different modes, the time of travel will be equalized. The transit time for a bit 1, 0, 1, that bit transit time will be equalized. So equalization of the transit time is happening in a graded index multimode optical fiber, and therefore on an average it can take, for example, one of the order gigabits per second. There's no bit interval requirement here, but here invariably there's bit interval requirement. Now, let me in this context speak about advantage Kochi. You know, Kochi is a very interesting city where we have 2 intercontinental submarine information superhighways established based on step index single mode optical fibers, makes its landfall. Landfall means most of the time these particular optical fiber cables will be traveling under sea, and it meets the land. That's what it's called landfall. These optical fiber cables are respectively C, Me, V3 and SAFE, two superhighways. This is the name of the highway. Name of the optical fiber constructor information superhighways are named like this. The first one you can see Southeast Asia, Middle East, Western Europe. It starts from Southeast Asia, Japan, and it travels to Middle East, Arabian countries, and reaches the Western Europe, reaching North Germany. You also see there is a third. In fact, there are 4 such superhighways in the same path, same route. So out of which this is the one of the important superhighways. And the second superhighway making its landfall in Kochi is SAFE, South Africa Far East. It starts from South Africa and reaches till Malaysia. So Kochi is blessed with 2 such optical fiber hubs or optical fiber landfalls. So almost 70% of data transfer happening in India is happening through these 2 superhighways. So we have therefore very important role in the optical fiber or internet or WWW World Wide Web map. That is something we have to always keep in mind. Kochi is having a great advantage with respect to optical fiber connectivity. And I have told you in the very beginning, almost 90% of the communication happening in the world today is happening through the optical fiber. And the basis of this particular construction of this optical fiber intercontinental submarine information superhighways is step index single mode optical fiber. It is generally costly, but at the same time it can carry large amount of data. And not only you can, for example, we'll see that later on, that large number of differing wavelengths, different channels can be passing a single optical fiber. Up to 160 channels can be accommodated to the single optical fiber. And not only that, you can carry the data in both directions in the optical fiber. So the amount of data an optical fiber can carry is amazing. And I repeat, Kochi is having a great advantage because we have 2 important submarine intercontinental information superhighways making its hubs in Kochi. Finally, let's discuss about some of the applications of optical fibers. So far, we were mainly concentrating on one of the most important applications of optical fibers, which is in the optical fiber communication. So as a communication system, every communication system, as we have already seen, will be having a transmitter, a receiver, and a cable or a channel connecting transmitter and receiver. And this is optical data which we want to communicate. And therefore, the transmitter has a primary job of converting any information to optical information, which means optical bits, optical zeros and optical ones, on-off information. Now, what is done is that any information given is first transformed into electrical bits, electrical digits, electrical ones and electrical zero. I already told you electrical ones means high voltage and zero means low voltage. Now therefore, any information you want to communicate has to be first transformed into digitalized to zeros and ones. And that zeros and ones is primarily connected to either to LED, which I have discussed, or to semiconductor laser. So, when the input of LED and laser is so connected, it will be also converted to optical information. LED will be on, or laser will be on, off. So, that in any information, which is digital information, will be translated into optical digital information, on-off information. And that on-off information will be fed to the optical fiber cable. We have discussed about it. And it will be carried to the receiver side. On the receiver side, there should be some photo detectors. So detectors we have already seen. They could be either PN junction photodiode, or you can have PIN photodiode. We have discussed all about them. There will be another versions also for the same. And the purpose here in the receiver side will be to convert the optical information, optical zeros and ones, to normal information. First, electrical information, electrical zeros and ones will be converted, and then it will be filtered, modified, everything is done to recover the original signal. So this is what is called communication. The perfection of the communication is that what we receive at the end product of this particular all processes will be exactly the original information. Then there is no information loss. So that is the aim, and a lot of work has been done to improve this. And I have already told you 90% of the communication worldwide is happening through around 50,000 times. It is said these optical fiber cables are winding around this globe, creating a backbone for the WWW, World Wide Web, all OFCs. So they are making worldwide web for communication. So the communication is the most ultimate, absolutely important application of optical fiber cables. I have not discussed everything about how transmitter works and receiver works. This will be discussed further in your individual classes by professors. Now, the second major application of optical fiber cables is they are used in optical fiber sensors. The optical fibers are, we have already seen, very small in size. Maybe 250 micrometer is their size. And their weight is very small. And thirdly, they are insulating, electrically insulators. Application of these optical fiber cables is, as I've told you, it is optical fiber communication. Now, but that is not the only application. Optical fibers are very much used as sensors also. The advantage of optical fibers are that they are very small in size. The diameters are very small, maximum 250 micrometer. But the core cladding together will be, you can reduce it further. Their weight will be also very small. And electrically they are insulators. They are mainly made of glass, so they're electrically insulating. And they are not allowing electromagnetic interference. And therefore the communication through the optical fiber channels will be excellent, and therefore they could be excellently used as the optical fiber sensors. Now, when we speak about optical fiber sensors, you can use these optical fibers in two ways. Either you can have a passive optical fiber sensor or extrinsic optical fiber sensors, where you do not change any properties of the optical fiber, rather they are used just as a channel for information, optical information. So there are large number of applications like that. For example, you have optical fiber bundles. You have large number of optical fibers made into bundles. And medically, they are used as endoscopes. You can examine any part of your body, your stomach, your heart, passing this particular thing through your veins. So this is endoscopes. or directly swallowing this, you can examine your stomach, for example. And very complicated measurements it can make. For example, when you're flying in an aeroplane, the temperature of the engine of the aeroplane is very important. And it's very difficult to measure. And therefore, you can put a sensor, a bundle there, which will be carrying the information about the temperature, the thermal radiations it creates, and there will be outside the engine, there will be a pyranometer, which will be giving you the information about the temperature of this particular engine of the aircraft. Or another example, you can think about a transformer core, where the temperature is very critical. The transformer burning will happen if the temperature is crossing certain limit, and therefore you can put the same cables there, optical fiber sensor cables, in a passive manner, which will carry the information about the thermal input, thermal radiation input, which will be telling you the temperature of this particular core of the transformer. And you can think about a conveyor belt where many things are Amazon, many packets are sent. You can count the numbers, the counters in the conveyor belts. You can make passive sensors. So basically, the properties of the optical fibers are not changing in this measurement. But you can make these optical fibers in an active manner also, intrinsic manner. So intrinsic sensors or active sensors can be made out of optical fibers, where we change some parameters, some properties of the optical fiber for measurement. For example, we can change the intensity of the optical fiber, intensity of light passing through. So intensity can be lost, we have already seen, by attenuation losses, intensity losses. If you make a lot of bending for the optical fibers, intensity will be lost. So this allows you to use these optical fibers as pressure sensors. When you put weight, the pressure will be, the bending will be happening, and the intensities will be lost. And you can measure the pressure, or you can make acoustic sensors, for example. Another property of the light is the pace of the light. You can change the paces for different measurements. For example, you can make gyroscopes based on this idea. The polarization of the light, if you use polarized light, you can change the polarization of the light, and you can have current sensors, for example. I'm not going to details of different sensors, which are active sensors, which can be made out of optical fiber cables. You can surf in the internet and get details, or the classes of the teachers on this will be giving you more details. My purpose is to give an overview of things, and I conclude our session on the fifth module. To conclude, we have seen three important things here. We started with the superconductivity, and then we came to optonics or photonics, and then we came to the optical fiber. And the last two sessions are interconnected, because photonics is made for optical fiber cables, or in other words, photonics together with optical fiber cables makes this optical fiber communication system and optical fiber sensors. Thank you so much.